Good morning, everyone. Good afternoon, good evening, wherever you may be. Thank you for joining us once again for a tutorial or a training session on, today we'll talk about FuelCell, and specifically we're going to talk about the instrument configuration. So we're going to go through how to set up the software so it matches the hardware that that you or the customer is working with. So I'm going to go ahead and share my screen, and you will not have to look at me anymore. Let's go ahead and start. We'll start the program. FuelCell. Just going to click through the first couple of buttons, and all right, so everyone should see the FuelCell window. Marion, is there anything you want me to do? Minimize anything, or I don't have the people showing up or anything?
Nope, it looks great.
Great. Okay. All right. So this is FuelCell, as we all know, and I want to note a couple things. First of all, this is about as basic as it gets in terms of setup. And as we add different accessories and devices that get controlled through the software, we're going to get some additional buttons and different things will show up. So, for example, as we add an auto back pressure unit, we'll have a apply pressure button will show up here. As we add a potentiostat button will show up here, and other sort of things as we add different components. I'm going to show you the setup fuel menu. This is about as basic as the FuelCell, the setup fuel menu gets. All we have right now is the ability to control the anode and cathode flow in a fixed manner, or in a load-based manner, but we have to type in the actual quantity of fuel and oxidant in terms of liters per minute per amp per cell. So this case would be, basically 10 or 11 cc's per minute per amp per cell. So we can't type in a stoichiometric amount, and that's because at this point we haven't told FuelCell what kind of reactants we're working with. Hydrogen, typically that's the most common thing for the anode, but on the cathode it could be air, which again is only 21% oxygen, or it could be pure oxygen, or it could be something else. So for the FuelCell to do stoichiometric based control, where we're providing fuel as a multiplier of the amount that's required to maintain the current, it has to know what it's actually providing to the cell. So until we set up the type of reactants, we're not going to be able to do stoichiometric flow, only load-based flow, but we actually type in the amount itself. And then finally, of course, we have the humidifier temperatures, which are going to set the dew point or the water content of the gas, which ultimately is going to affect the relative humidity that the fuel cell sees. All right, so this is about as basic as it gets. And as we add different accessories and different options, this menu will get more populated and more complicated. It will give us more ability to control things. All right, so let's go to the instrument configuration. So typically, this is something that you want to do whenever you go to a customer site and either are just visiting them and checking up on them, just to make sure that the instrument is configured to match the hardware. Also, if you're doing a new installation, there are some automatically like default properties of the test system that are assumed to be in place when you install, for example, an 850, a 50 amp unit versus a 100 amp unit. Most importantly would be the mass flow controller size. But what you want to do is you do want to go in and just verify that the actual instrument configuration matches the physical hardware that is part of the setup. So it's just file instrument configuration. I've mentioned this before. Typically, you would type in the instrument's serial number. In this case, we're going to use the universal cheat code of -999. And here we are. So this is the instrument configuration, the setup instrument. Each tab is described in detail in the manual. So we've got, it looks like about 8 tabs here: fuel configuration, an auto multigas, and I'll go through all of these individually. So let's start with the fuel configuration. This is going to define in part what shows up in the setup fuel menu, or the change fuel experiment step. It's broken into 2 sections. The top section is the anode side, the bottom section is the cathode side. And you can see we can choose basically the fuel type or the fuel flow control type. Typically, it's going to be a mass flow controller if you're providing a gas to the cell, but you have the option of providing using a pump if it's a liquid fuel cell. For example, it might be a direct methanol fuel cell in which you're feeding a methanol solution to the cell. So you would switch over to using a pump, and then you just define things like the full flow of the pump. Typically, it's going to be on the Reformate channel number 1. These would be defined by the labeling on the cable, or if there's questions, you can contact us. But I think typically a pump would be on Reformate channel number 1. And then depending on the specifics of the pump, there may be an offset control and then a minimum value. But for now, let's stick with gas. So we've got let's do a typical 850 installation where we've got one mass flow controller on the anode, one mass flow controller on the cathode. Typically, the anode is going to be a hydrogen mass flow controller. The cathode is going to be an air mass flow controller. And the main thing what you want to check here is just to verify that the size of the mass flow controller, meaning the full flow rate of the mass flow controller matches the hardware. And if you recall, the back of an 850 or an 840 or other products, they all have what we call a serial plate, or a sticker, if you will, that sort of defines or describes some of the things about the hardware that you're working with. So in this case, this is an example of an 850E serial plate, and this there's a serial number. There's the load rating, and what we're looking for right now is the mass flow controller size. So anode and cathode flow. This particular unit has a 2 liter, or standard liters per minute, of hydrogen, and a 5 liter, or standard liters per minute, SLPM, air mass flow controller on the anode and cathode respectively. So what we would want to do is we would I guess I can't, whenever I click over to this, it's going to go away, but we want to make sure that the mass flow controllers here match the mass flow controllers shown here, because this is physically what's in the hardware. So in this case, it would be wrong, right? And we would get incorrect flow rates. We've got a 1 liter full flow, but it's actually a 2 liter full flow. So we would just update this 2 and 5, right, to match the hardware, right? So that's pretty simple. And then we have a few different boxes we can select here. If the unit has the wet, dry humidifier bypass solenoids installed, again, this is a hardware installation, we would want to check those buttons to enable them. And we've sometimes seen people that check the box, but the hardware doesn't actually have it. So they enable it, but the system doesn't physically have the hardware, so it doesn't actually do anything, but they don't know that. Again, checking the serial plate will tell you that. Under options at the bottom, WD means wet dry. The 880, 881 FRA means it's got impedance. AWF is auto water fill. HT is high temperature. And each of these acronyms is defined in the 850 installation manual. So if you go to the installation document and you're wondering how to interpret the serial plate, it's described in that document, and you should look there. So coming back to, so this unit does have the wet dry humidifier bypass option installed. And so it would make sense for us to enable those solenoids in the software. Again, remember, the software doesn't know anything about the physical hardware that it's working with, right? It's only going to be as smart as you configure it to be. So we have to tell it that it's got the solenoids installed for the humidifier bypass, meaning that we can provide either wet gas, i.e. humidified gas, or we can bypass the humidifiers and provide dry hydrogen and air to the fuel cell to run in dry mode. And you'll see how that shows up in the fuel menu in a second. We recently added the ability to ramp flows. There's only one button in the anode section. We don't have anode and cathode independent, so you either enable it or disable it within the the anode section, but it applies to both anode and cathode. And this allows you to, or allows the customer to change when they change flow rates. It's going to ramp from the current flow set point to the new target set point at a certain rate. And you'll see how that shows up in the menu, as opposed to doing like a step change. So some people don't want to do very rapid changes in flow. They'd rather have a controlled rate of change of flow when going from one point to another. And I'll show you how that shows up. And then finally, we can apply, if we tell the software what kind of fuel or reactants we're working with, then it allows us to do stoichiometric control. And so hydrogen is the typical anode fuel. And we could pick something else. If we say it was methanol and we knew the concentration of methanol, then we could type in a certain value here. We'd have to do the calculation ourselves. But in this case, we've got hydrogen, pure hydrogen. And if we recall our basic Faraday's reaction, we can calculate that it takes 7 standard cubic centimeters per minute to maintain 1 amp of current. And so that would be a stoichiometry of 1. In this case, we've got a pure fraction of 1 because it's pure hydrogen. On the cathode, let's choose the example of pure oxygen just for a second. We consume 2 hydrogens for every oxygen, so we're going to need 3.5, or in other words, half of 7, 3.5 cubic centimeters, standard cubic centimeters per minute to maintain 1 amp of current per cell. And the pure fraction would be 1 if it's pure oxygen. If we choose air instead, which is a more common oxidant, then now we've still got the same stoichiometric factor because we're still reacting oxygen, but it's only 21%. And so that's going to factor into the calculation when we're determining how much air we have to flow. First, we determine how much oxygen we have to flow, and then we take into account the fact that it's only 21%. So let's see what happens when we save this and how the fuel menu changes as a result. So again, every time we change instrument configuration, we have to restart the software to get those changes to take effect. Okay, so now the fuel menu is going to look a lot more complicated, a lot more available options. Coming back to the flow type, where we can still do fixed flow, but now we can still do load-based flow, but we also have the ability now to do stoichiometric flow, because now we've configured the software that we were working with hydrogen and air, and so it knows what the stoichiometric factors are, the 7 cc's and the 3.5 cc's for oxygen, or it turns out to be about 16 or 17 of air. And so we can type in an actual stoichiometric factor, right? So there's our number 7. If we type in a stoichiometric factor of 2, that's going to double it, right? 14. So now we can control we don't have to type in an actual load-based value. We can type in just a stoichiometric factor. There's our ramping control. So if we want to control the rate of change of flow, it's going to be in liters per minute, right? Because the flow rate is liters per minute, and then we're going to do that over a certain time period per minute. And so it could be, for example, a liter per minute and they're independent anode and cathode flow control, and to basically sort of bypass it, if you will, or not do ramp changes in flow, just put a 0 in, and then it'll apply the new flow rate instantaneously. So you'll get more of a step change in flow rate as opposed to ramping. So basically 0 disables it, or basically ignores the ramp rate. Again, our humidifier temperature set points, and then we enabled the wet dry solenoids. So so we can bypass the humidifier if we want. So dry refers to when the fuel will not go through the humidifier and will proceed directly to the cell. And in the wet case, the gas does go through the humidifier, picks up water vapor, and will proceed to the cell. So now we've got a few more options available. All right, so now we're going to go back to the instrument configuration and look at the next tab. Okay, so that's fuel configuration, a really, really important tab. You definitely want to verify primarily that the mass flow controllers are the right size. The second tab is auto multigas. Okay, so those who may not be familiar, just very briefly, the auto multigas is an accessory. This is an example of an auto multigas for an 850. For an 840, it's built in. It's a standard, so it's internal to the device. Basically, it's a series of solenoid valves that allow the user, the customer, to connect up to 3 gases on the anode side and 3 gases on the cathode. Let's see if I can make this a bit bigger. All right, so you can have up to 3 gases on the anode A, B, and C, and cathode A, B, and C. And this is for switching between gases. This is not for gas mixing. We'll get to gas mixing in a minute. This is for switching between gases. A very common thing to do in fuel cell testing, at least within PEM testing, is to switch between, say, hydrogen, on the cathode, switch between air and oxygen, for example, testing with pure oxygen versus testing with air, but also running with nitrogen on the cathode for certain diagnostics. And so instead of having to connect and disconnect your nitrogen supply to your cathode inlet, we can automatically switch between those gases by having both air and nitrogen and oxygen connected to the cathode as an example. And so this is how it looks as it's installed. It's kind of a muddled picture. I do apologize for that, but this is basically the auto multigas accessory. It's a very common accessory. It's very useful in terms of providing the hands-free ability to switch between reactants that the cell is being fed. So this is where we configure it. It is a device that's controlled through the software. And so auto multigas, the typical 99% of customers are going to have a 3-port. That's the one that I just showed you. And now we can enable up to 3 gases on the anode and 3 on the cathode. Whether or not they show up is available in the setup fuel menu will be defined whether there's a checkbox or not. And so let's just do an example. So typically it's going to be hydrogen on the, doesn't have to be on the A port, but let's just, a common example, this is how we typically set it up here. So we've got hydrogen connected to the A port. It's going to be pure hydrogen. So we have a pure fraction of 1. In this case, the mass flow controller, because remember, the gas is still going to flow through the main anode and cathode mass flow controller. The mass flow controller itself is a hydrogen controller, so we have no flow correction. Now, this is basically where we would put in like a gas correction factor if we were trying to flow, say, methane as an example, instead of hydrogen as the fuel. We might have to adjust the flow control factor to account for the fact that it's methane flowing through a hydrogen controller. And so you could look up the gas correction factor in the flow controller manual itself and figure that out. We've got app notes on our website, and you can always let us know if you have any questions about that. So in this case, let's say we're going to have nitrogen connected to the port B. Say we want to be able to provide nitrogen to the fuel cell as well, but with the fuel turned on. In this case, the pure fraction is going to be 0. There's no, it's pure nitrogen, but this pure fraction really refers to the fuel content, if you will, the reactive component within that. And so, and it's really used for stoichiometric or load-based calculations. Well, I guess stoichiometric, really, not load-based. You can still do load-based flow just by typing in a number, but it's really for stoichiometric calculations. In this case, we would want to type 0 because there is no reactive component within nitrogen. The flow correction can just be left as 1 in this case. We're not going to use port C because we're not going to have a 3rd gas connected to the anode. And let's just do a typical example on the cathode. where we have air. Now, in this case, again, the pure fraction relates to the reactive component within that gas. Again, it's oxygen within the air, which is the reactive component. It's 21%. So we'll type in 0.21. That's a air mass flow controller, so the flow correction is going to be 1. No correction required at all. Let's say we have nitrogen on the port B. It's got a reactive component of 0. Again, no correction required. And let's just pretend we've got pure oxygen on port C. It is pure oxygen, so the reactive component, the pure fraction is going to be 1, and we don't need to do any flow correction. If you look up the gas correction factor for air, nitrogen, and oxygen, they're all basically 1, and so you don't really have to apply any flow correction. All right, so now we've set up the auto multigas. And let's see what that does to our setup fuel menu. Okay. All right, so now nothing else has changed. Well, we've got pretty much looks the same, except we have one new section, which has been added for the auto multigas. And you can see we've got the ability to switch between hydrogen and nitrogen in an automated fashion through the software, because we're activating solenoid valves. We're activating these solenoid valves. There's 2 solenoid valves on the anode side and 2 on the cathode side that allow us to switch between these 3 different gases. And so now we can switch gases in an automated fashion, so we can create experiment lists where we can actually switch between different gases as part of an automated test program. So that's the auto multigas, fairly simple. Here we go. Here's a good example. So I've switched to nitrogen, but I'm trying to use, it's saying, but I've also got stoichiometric flow control selected, and it's saying, well, you can't do stoich control with an inert gas. There's no reactive component. You've told me there's no reactive component in there, and so I end up dividing by 0, and I can't do that. So hey, you better be either switching the gas type or moving over to a fixed flow. And so I'd have to be saying fixed flow, which makes sense. You're not going to run under stoichiometric control if you've got nitrogen instead of hydrogen as the reactant on the anode, because you can't have current, right? You're not going to have current, so you can't really have stoichiometric flow anyways. So you'd be on a fixed flow, for example. So that's the auto multigas. So next, we'll go to the next tab. All right, so that's auto multigas. That's gas switching, right? So we're switching gases. We're not mixing gases, and people often get this a little bit confused. So next we have gas mixing, or what legacy terminology is Reformate, or Reformate simulation. So this is for mixing gases. Now in this case, the appropriate accessory is the 850R gas mixing interface, and this is what it looks like. So this is an external accessory that will be connected to the test system, and this allows for gas mixing. So you've got 1 or more mass flow controllers would be on this box. Each is assigned to a unique channel. We call it Reformate channel 1, 2, 3, etc. And then it's got its own gas supply, and then that will be connected to the test system or the cell in some way. So on the back of the 850, we've got 2 additional ports that are labeled cathode mix and anode mix, and that plumbing goes and tees into the at the outlet of the main mass flow controller in the test system. Tees in, and then would then proceed either through the humidifier to the cell, or you can bypass the humidifier and go to the cell. And so there's dedicated plumbing for mixing of additional gases into the anode or into the main anode or cathode fuels using additional mass flow controllers, and those are going to be external. You can also plumb the outlet of this mass flow controller directly to the cell itself if you don't want the gas to go through the test system. So an example here would be like a corrosive gas, maybe like a NOx or a SOx, sulfur dioxide, something like that, or H2S, or another common one would be carbon monoxide. Sometimes people do testing with carbon monoxide, and that tends to absorb onto the surfaces of the humidifier and all the tubing. And then when you switch back to a carbon monoxide free environment, typically it's gonna be like carbon monoxide in hydrogen. If you switch back to, say you're doing CO poisoning, you wanna switch back to doing CO free pure hydrogen testing. It takes time to purge all of that adsorbed CO out of the system. And so you have to, wait for some period of time until you can go back to, you recover the cell performance and you go back to testing with pure hydrogen. It just takes a while to get rid of it. So you might want to dump that carbon monoxide in at the cell inlet instead of having to go through the test system, in which case you'd have your gas plumbed to the mass flow controller, and then the outlet of the mass flow controller would go directly to the inlet of the fuel cell, and you'd be bypassing the 850 completely. So of course, this device and what gases are connected to it, how many mass flow controllers, which channel, and then whether the gases are plumbed to the anode or cathode, the software doesn't know. And so we have to tell it, and we have to configure the software. And that's what the gas mixing / Reformate tab is for. So the first thing we do is we tell it that we have one. So typically it's going to be the standard. That's just going to be an 850R gas mixing interface with one or more mass flow controllers. We can choose to display the gas mixing is in percent or parts per million. And I'll kind of explain a little bit about the when we might want to choose one over the other in a few minutes. Let's stick with percent for the moment. We're still going to tell it that we got hydrogen and air as my main gases. And let's just pretend that we've got on the anodes, let's say we're doing CO poisoning studies, right? So carbon monoxide is a poison to a low temperature PEM fuel cell where we're using platinum as a catalyst. Basically, the carbon monoxide will sit on the platinum surface and physically block the hydrogen from getting to the platinum surface, and it degrades performance. And so we often want to, let's say the goal of my study is to look at effect of carbon monoxide concentration on the performance of my cell. And so I would have a tank of, typically you're not going to buy pure CO, you're going to buy a tank of CO, carbon monoxide in hydrogen, at the highest level or higher than I want to test at. And then I'm going to be able to dilute that carbon monoxide in hydrogen with another pure hydrogen gas, right? So my main anode has pure hydrogen, and then I'm going to mix my CO containing hydrogen with pure hydrogen to end up with the final concentration of hydrogen of carbon monoxide that I want. So let's just say I've got hydrogen and CO. The gas is going to be carbon monoxide. That's what I'm interested in. I'm actually going to change to parts per million, because in this case, with impurity studies, typically we're going to be looking at parts per million. That's the sort of the unit of interest. So I have to tell it basically just a descriptor. I'm going to plumb that gas to the anode. I have a choice of unused anode or cathode. So on the mass flow controller itself, it would say like Reformate number 1 or tank number 1. So I know that on the 850R, this mass flow controller is assigned to or connected to Reformate channel number 1. So that's the signal that I'm going to be using. And let's just say the concentration, the mass flow controller itself is say 200 cc's or 0.2 liters per minute. Let's say I'm interested in from 0 ppm up to say 100 ppm. So maybe I buy a tank that is like 200 ppm. And in this case, I have a pure fraction of, this is for stoich control. So I think we want to type in a pure fraction of either 0 or 1. I always forget exactly whether you want to have a 0 or a 1 if you're working with like an impurity like that. I think you want to type in 1. I'd have to look I'd have to remind myself exactly how these work, but if this was nitrogen, we would put a pure fraction of, well, if it was, yeah, I think I'd still leave it as 1. So let's just say I'm going to use unused. So I only have, in this example, I've got one external mass flow controller. Nope, is that tank 2? Yeah, okay. Yeah, I'm going to unuse. So I don't have additional options show up that I can't really use. So in this example, I've got one extra mass flow controller with a connected to a tank of hydrogen with 200 ppm of carbon monoxide. And let's see how that shows up. Okay, so now I have one more section. I only have gas mixing on the anode. I didn't configure anything on the cathode because in this case I don't have anything on the cathode. And the way it works is now I can type in a final ppm, final concentration of carbon monoxide that I want, and then the software will take it from there. So as an example, let's say I have a flow rate of 0.2 liters per minute, and I want to end up with a final concentration of carbon monoxide of 50 ppm. All right, so what the software is going to do is it knows that the full concentration of the concentration of CO in my tank is 200. So it says I have to basically dilute that by a factor of 4, right? Or go from 200 to 50. So it's a dilution factor of 4. The total flow rate is 0.2. So I'm going to feed 0.05 liters per minute of the hydrogen with CO in it, and 0.15 liters per minute of pure hydrogen, and that's going to give me a final concentration of 50 ppm. So that's how that would work. All right, so it's important to note that when you're working with mixing gases, it only applies when the fuel is turned on. Right, so basically the mixing gases will essentially be disabled. The external mass flow controllers will not be operated when the fuel is turned off. Remember, the fuel is turned off, we're only flowing purge gas on both sides. So the fuel has to be turned on before we would be able to start actually mixing gases, and that makes sense. In this case, I wouldn't want nitrogen, right? So I'd want hydrogen to be my main gas. So my main gas coming through the auto multi-gas is going to be hydrogen. That's pure hydrogen. And then I'm diluting that into, or I'm taking that and diluting it with the hydrogen that has the carbon monoxide to end up with the final concentration that I want. So that's an example where we're using ppm, parts per million. Another typical example would be common these days is looking at the oxygen transport resistance within the cathode. And so for those tests, we're basically looking at what they do is they dilute. You want to create mixtures of nitrogen and oxygen to get different concentrations of oxygen. And so we can start with 21. We can start with pure oxygen, but we can also take air, which is mostly nitrogen, dilute air with additional nitrogen, and end up getting lower and lower concentrations of oxygen. Do these what they call mass transport limiting experiments, and you end up getting something called the oxygen transport resistance. So it's the resistance to oxygen diffusion through the gas diffusion media, as well as the catalyst layer pores, basically. And in this case, let's pretend that we've got on the cathode, we have another mass flow controller. This is going to be we've got nitrogen, and let's say it's a 1 liter controller. Now in this case, it's pure nitrogen, so the concentration in parts per million is 1,000,000, right? So the pure nitrogen, the concentration in parts per million is 1,000,000 parts per million. And the pure fraction this time would be 0 because there's no reactive component to it. And we're typically going to do percent instead of ppm. You could still do ppm if you wanted to, but it makes more sense, and you'll see in a second, where we're really controlling the amount of oxygen in a percent wise, not so much in a ppm. It's easier to just think about it in terms of percent. So I'm going to disable this one just so it's a little bit clearer. So example, nitrogen on the cathode, channel number 2. It's a 1 liter controller with pure nitrogen. Save. Again, it's still this still this 850R gas mixing interface, the same kind of hardware, but now that would be a 1 liter nitrogen controller, for example. At least that's what I said, and it would be assigned to channel number 2. And so now, typically these experiments are run with fixed flow rates, and now I can dilute. Now I can add nitrogen to my air, right? So my main gas is going to be air, and I'm basically diluting air, which is 21% oxygen, with pure nitrogen to end up with some final concentration of oxygen. So in this case, for example, let's say, now in this case, you have to do the math is a little bit different. You're thinking about what's the percentage of the nitrogen do I want, right? What percentage of nitrogen? So let's say I want to go from 21% oxygen, which is in air, to 2.1% oxygen, right? So I'm diluting the oxygen by a factor of 10. That means that I want 90% nitrogen, and then it's going to know, the software will know that I'm going to provide 900 cc's or 0.9 liters of pure nitrogen, 0.1 liter of air, and that's going to end up with a decrease in the oxygen concentration from 21% down to 2.1%, so a factor of 10 dilution. If I wanted to cut the oxygen concentration by a factor of 2, say from 21 to 10.5, then that's a factor of 2 dilution, right? So I'm going to have 50% pure nitrogen, and then the software will know that the remainder is going to come from the main gas, which in this case would be air, right? So that's one way you can do it. You can also set it up differently. So you could basically put air as the mixing gas, choose nitrogen as the main gas, and then you're actually dealing with oxygen concentration. In that case, you're actually just typing in the final oxygen concentration. So maybe we can do that instead. Let's see here. That's an easier way to think about it. It all depends on how you want to do it. So let's say I'm going to switch to nitrogen as my main gas. And let's say I have air and my reactive component. This is what I'm going to be controlling it for. Now, in this case, it's 0.21. Actually, it's pure air, so it's still that. And I think we want to do 0.21 here. I think that's the way it would work. Maybe not, I'm not sure. I think actually it would be 0.21 and the pure fraction would be 1. I think that's what you want to do, because that's the constant. So in ppm, so it would be 2.1. What is it? 210,000, right? 210,000 ppm is 21%. So that's the concentration of oxygen. And then, yeah, I think this is the way you set it up. So let's do this. It gets complicated when you're dealing with both the sort of stoichiometric control type and the concentration effect. But it's described in the manuals. So in this case, so now I think we want to type in, let's say 2.1%. Yeah, we've got, and so we've got nitrogen is our main gas. And now we just type in a final concentration of oxygen. It knows that it's 21% to start because we said it was 210,000 ppm. And so it would know that basically it would have to go from 21% to 2.1. It knows that's a 10-to-1 dilution. So it would provide, in this case, it would provide 10% of the air and dilute that with 90% nitrogen, which is the main gas. So there's different ways you can configure it, and then you have to do a little bit of thinking about how or what you're actually typing in here, depending on whether you're the diluting gas, what it is and what you're trying to get to. So we can have multiple. As I mentioned, this was designed originally a long time ago. People were talking about doing something called Reformate, which is taking natural gas or methane, CH4, and converting it into a mixture of hydrogen, carbon monoxide, carbon dioxide, and water, and that was the fuel that would be fed to the fuel cell. It's kind of gotten out of fashion now, is onboard Reformate production, basically converting natural gas, but it's still around. And so what people would do is they would have mixtures of hydrogen it'd be CO2 in hydrogen. This would actually be CO in hydrogen. And so CO2 would be the amount in this case. I don't know. I don't have a good feel for what concentrations. I think they're like a few ppm. So let's say it's going to be 10%, just as an example. So that would be 1 e to the 5. That would be 10%. And so that would be, and this would typically be on the anode. So we're going to do something called Reformate simulation, where we would be making a mixture of hydrogen, CO, and CO2. We're looking at the effects of different concentrations, different mixture amounts, and we want to basically just generate that by mixing pure hydrogen with hydrogen that has CO in it, hydrogen that has CO2 in it, and then by controlling the dew point, the water vapor content, we can also control the H2O content. So we're making a synthetic mixture of a Reformate gas, or the product of a Reformate process. And so this is called Reformate simulation, and that's why we call this Reformate. This is a holdover from probably 20 years ago, 15 years ago, when Reformate was more of an interest in the PEM fuel cell community. Maybe it'll make a comeback. So now it's more generically gas mixing, but it's the same concept anyways. So again, in this case, now we're going to be able to just have, now we'll be able to mix multiple gases. I know it seems like we're starting and stopping the software a lot. Again, typically the equipment setup doesn't really change a lot, and so we're not typically doing this on a daily basis. At least from typically for most customers, they're not adding and subtracting different components a lot on a daily basis. So we're not really, the customer isn't generally having to restart the program a lot. Typically, only once you set it up, and then once you make changes. And that's only sort of periodically. So now we have an example here where we've got hydrogen, and then we can say, oh, I should have probably converted it back to ppm. We could type in a final parts per million or percent of CO and CO2, and it's going to do the gas mixing from there, right? So that would be a Reformate simulation sort of example. And you can have mass flow controllers on both anode and cathode, right? So for an 850, you can have up to 3 additional mass flow controllers if there are 2 mass flow controllers internal. So just think an 850 can have 5 mass flow controllers operating at one time. It can take, that's how many it can control. 2 internal typically, and then 3 external. That's typical. If you're working with an 890, it's more. I believe it's 7 mass flow controllers in total. But so let's come back to here, right? So your external device can have, I think this device can hold up to 5, but when working with an 850, you would only be using 3 at one time. You can only control 3 of them at one time. And you can mix and match in terms of anode and cathode and etc. So that's the example of gas mixing. So now you can see our fuel menu's gotten a lot more complicated, right? We've got a lot more going on. We can do stoich control, we can ramp flows, we can mix gases, we can switch gases, and we can do humidifier bypass. We can provide dry or wet gas to the test system, right? So that's a much more advanced. A lot of accessories have been sort of added to the system, but this is not an uncommon situation these days. A lot of people are getting a lot of accessories and options that give them a lot more flexibility. And of course, this shows up. Yeah, okay. So it can't do stoich control with inert gas. Okay. And of course, this shows up not just in the setup fuel menu, but as a change fuel experiment, right? So anything, basically, this is like opening the setup fuel menu. All of these different options are available as an experiment step. So we could change concentrations of CO and CO2. We could switch gas types. For example, we could switch between wet and dry. All of these kinds of things can also be affected as an experiment step. Okay, so the next thing is, the next tab is gas mixing. So this is a recent one, auto back pressure. So this has only probably been available in the last few releases of FuelCell. So if you don't see it in a customer's setup instrument window, it's because they have a version that's a little bit older than what's currently available. And if you just update the software, it will become available. So this is a new, a relatively new configuration tab within FuelCell. Before, we had to go in and edit the INI file, a configuration file, add some text to the FuelCell.ini configuration file to enable the automatic back pressure. And so what is an automatic back pressure? This is a accessory that allows you to control the pressure of the reactant that the cell is operating at. So you can elevate the pressure that the cell is operating at, hydrogen and air, for example, to look at the effect of pressure on the performance of the cell. And so this is we have a manual version, which we don't configure in the software because it's not controlling it. It doesn't really know anything about the pressure in that case. But if you have the automated version, you can set the pressure in an automated fashion, change pressure as a function, as part of a test list, et cetera, et cetera. So this is the floor standing. I don't know if I have some other pictures here. Yeah, this one shows it sort of as it's installed here in our lab. So this is a floor standing back pressure test system. It's got connection to the test system, obviously. It's got your anode and cathode. This is coming from the cell. This is your vents. These are the auto draining tanks at the bottom here. 2 controllers for controlling the pressure, and then there's a pilot gas that uses either nitrogen or air, some relatively benign gas for providing the control of the back pressure. So that's the back pressure, auto back pressure unit, and because it's controlled through the software, we need to set it up. So there's some old flavors that are out there. Typically, you're not going to be dealing with these. You're gonna, if it's one of what I just showed you, that's a Scribner auto back pressure system. It comes pre-configured, and so it's just like the controllers and everything are already pre-programmed in there, and it's just a matter of basically setting sort of the maximums and the units. So the default is kPa. That's typically what I like to work in. Recommend starting in the only other option is PSI, and that's mostly for people here in the US who like to work in pounds per square inch. Most people are going to work in kPa. The maximum is 310. That turns out to be I think just shy of 45 psi. It's about 3 bar gauge. You wouldn't typically touch these values, and then there are some offsets. Typically, they're going to be a small positive or negative value. In fact, the offset value is going to be written on the manual that comes with the auto BP unit. So each one gets calibrated here at the company before it's sent out. We adjust the offset so that basically it's the 0 point, and we write that number on the manual. And during the configuration installation of the auto BP unit, we ask that the customer in here enter in those offset values. If they're left at 0, it's not typically a big deal, because typically the offset is a very small value. Typically, it's going to be somewhere between -2 or 3 and +2 or 3. So we're talking like just 1 or 2 kPa offset anyways. So it's not generally a big factor, but it is there. And that's pretty much it. If you are working with a customer that has a really old back pressure system, typically these will be like custom designed in-house. Probably the best thing, to be honest, is just to contact us and have us work with them to try and figure out what the proper settings are. There's not a lot of these out there, and they tend to be sort of power users anyways who design their own systems. So mostly it's going to be a Scribner auto back pressure system, and that's what you'll be working with. So now we've configured it. Exit. No. Okay, so see, now we have a new menu shows up. Set up pressure. That's a third menu that we see as we first start the software. I'm just going to click through it. And now we have a new button, a new apply pressure, right? So before we just had the 3 main: temperature, fuel, and load. Now we have a new pressure associated, a new button associated with pressure, right? So we can turn the pressure on and off, just like before. And we also have a new button in the background section associated with pressure. It should show up here as well. Apply pressure and setup pressure, right? So apply pressure is the same as pressing this button. Setup pressure is the same as clicking on this button. And now we have a menu associated with the control of the pressure, the back pressure, if you will. I'm not going to go through the details of this. That's not the point of this instruction. I would suggest you look at the FuelCell manual as to the description of what all these parameters are and do. So that's the setup pressure. And of course, now we'll have a new experiment as well. We'll have a change pressure, right? So we can change pressure on the fly, again, because this is an automated back pressure unit where we're controlling it through the software. So that would look just like the setup pressure menu, but this would be as an experiment step. So that's described in the manual as well. Looks like we're coming up on close to 1 hour. Why don't we take a short break? Marion, does that sound good to you?
Yes, I will
Okay.
pause the recording.
Okay, welcome back everybody to the second part, and we're going to continue with going through the instrument configuration window. We just finished the set up the auto BP, auto back pressure unit, and we've got a few more tabs to go through. Thank you for sticking with us. Yep, so we've covered fuel configuration, auto multigas, gas mixing and Reformate simulation, auto back pressure. And so we've covered 4, we've got about 4 or 5 more tabs. Some of these will go pretty quickly. So the system configuration, this is primarily going to be used for setting up additional temperature controllers, and where we can control ramping of the cell temperature as well. So for example, this is typically for high temperature fuel cell, something like a solid oxide fuel cell, where the cell is in a furnace that's going to go up to 800 to 1,000 degrees centigrade. Often that furnace has a lot of heating capability, and we don't want to basically set a set point of 1,000 degrees and let that temperature just take off as fast as it can. We typically want to ramp the temperature of the furnace up so that the cell heats up in a controlled manner. And in this case, we would just enable ramp cell temperature, and I'll show how that ends up in the setup cell menu. For low temperature fuel cells like a PEM cell, typically you want to heat as fast as you can. You're only going to go to 60, 80, 120 degrees, something like that. Even a high temperature PEM like a PBI, maybe up to 150, 180, 200 C. Typically, you're not too worried about controlling the ramp rate, in which case we're not going to control the rate of cell heating. We're just going to apply a set point, and the cell will heat up as fast as the heaters will allow it to, basically. But I'll show you what that does. Also, if you have an alarm, maybe you don't want the cell to cool as fast as it can. You want to ramp the temperature down, and again, that will be for like a solid oxide cell, mostly, not really a low temperature PEM type situation. But there is the option to ramp down as well if you ramp it up. Auxiliary temperature controller, this would be most commonly used. For example, we have an accessory where we can control the cell heating and cell cooling, if you will, using fans, and that can be temperature controlled. And so if you want to cool the cell like a PEM cell fixture rapidly from, say, 80 degrees down to near ambient, we can have an external temperature controller, external box with a temperature controller. That would be the auxiliary temperature controller. And then we can use that to run fans that blow air onto the cell fixture to cool it down in a relatively rapid manner, as opposed to just waiting for ambient cooling, where we can do basically forced air convection cooling. Each temperature controller is a serial device, and it has its own address. So this would just match the address on the temperature controller itself. These voltage control loop, current control loop, and power control loop speeds are basically just parameters associated with the control loop of the load in the 850 or the 890. Typically not something you're going to adjust. So yeah, just unless we tell you to, unless we specifically ask you to change one of these control loop speeds, typically we're not going to adjust that. Don't adjust the baud rate, and I'm not even sure what this is, to be honest, what that is. I'd have to look up what that is. Never used it. So let's see what happens when we restart the software now. So all we've done is add an additional temperature controller, and we've turned on the apply, the temperature ramping. So this is going to show up in the cell menu, and we've also got an additional temperature up here, right? So we've added another, what we call the auxiliary temperature. So we can set that value and we can turn that on or off. And the configuration or the control of that is going to be in the setup cell menu. And here's the auxiliary temperature. And so that could have its own independent temperature set point. And then it has and then we've also enabled the ramping, right? So this is temperature ramping. It's in seconds per degree centigrade. So typically we're going to ramp for like a solid oxide, 1 to 2 minutes per degree centigrade. That's about the ramp rate, or 1 degree centigrade per minute. So this would be something like 60 seconds, or if we're going to do 2 degrees centigrade per minute, then it would be 30 seconds, right? So that would give us a 2 degree per minute ramp rate. So that's a typical value for like a solid oxide. So that's the only change really, is we're ramping temperature, and we've added this auxiliary temperature controller. And of course that would show up in our change cell menu as well, right? So we can on the fly change what that auxiliary temperature would be. So instrument configuration, we'll go back in here, do the next tab. That's system configuration. That was the system configuration tab. The next tab is alarms. And the primary thing here are, at least within an 850 and on an 840, the humidifiers have a low water alarm associated with the water level in the humidifier. It's not a good thing to try and heat an empty tank, because there's there's a big disconnect, a thermal disconnect between the temperature probe, which is in the humidifier, typically is in water, and the heaters themselves, which are on the outside of the tank. If there's no water in the tank, it takes a long time for the heat that's put into the stainless steel tank to actually end up being registered as a thermocouple, which would be in air, if it's, or gas at least, if the tank is empty. And that means you can end up putting a lot of heat into those heaters and damaging them in the insulation prior to even registering a temperature change at the thermocouple, because it's in air or a gas, which is a relatively poor thermal conductor, as opposed to water, which is a fairly decent thermal conductor. And so you register that temperature rise relatively quickly. So so all that is to say, you don't want to apply temperature or try to heat up an empty humidifier. So the humidifiers have water level sensors in them, essentially. And if the water level falls to a certain point, it will trigger an alarm. And there's independent anode and cathode alarms. So there's 3 alarm signals basically available. One is the low water on the anode, one is low water on the cathode, and then depending on, there is some configuration as to the user can define what happens on a low water alarm situation. So for example, you could, the most conservative is to remove load, purge gases, and remove temperature, but maybe they just want to reduce the anode temperature, and because that's where the alarm took place. Same thing on the cathode. And then there is a third alarm, and this is typically going to be associated with some sort of external alarm, like a hydrogen detector or a combustible gas detector that's in the lab, that if it goes off, and it's connected to the test system itself through the auxiliary signals connector, then it can take action as well. So if we have a detection of hydrogen in the lab through some external hydrogen detector, then we typically would want to do the most conservative thing, which would be to switch to purge gas, reduce all temperatures, and put the system in a safe state. There are some other alarm sort of options here. So the 850 and the 840 have pressure sensors on their inlets. So let's see if I can find on the back of an 850. Well, I'm not gonna. So, you know, on an 850, we've got gases connected to our anode and our cathode, right? So our main hydrogen and air, for example, and then we've got a purge gas. So just beyond this back panel is a pressure sensor, and it's set to trigger at around 3 bar, something like that, 45 PSI for those familiar with American units or imperial units. So about 3 bar. If the gas pressure falls below that value, then that's typically it's not a good thing. In particular, the purge gas, and so we can have an alarm trigger based on that. You can disable them. So, for example, if let's say you have a test system that's working with liquid fuel on the anode, and you don't even have hydrogen available in the lab, and you don't have hydrogen connected to the anode input, you could disable that alarm so that you don't get an alarm based on the fact that there is no gas connected to it. That's certainly fair. It all depends sort of on the situation, but typically we don't like to disable these because they are there for safety.
Kevin,
And then,
sorry, we have a quick question on one of the alarms. If the auto water fill option is available, then are low water alarms needed on the anode and cathode?
so auto water fill is available on all test systems now. It's not an option anymore. There are some, if you're working with customers that have very old 850 systems where they only have manual water fill, then that's different. They'll still get an alarm. But basically, if the system, for people that have auto water fill systems, which is pretty much everybody nowadays, the intent is that or the requirement is that the test system have a source of pressurized water connected to it. And we describe what that pressure should be set at. And so so what happens instead of getting an alarm is that when the humidifier registers, when the test system registers that the water level has fallen to a certain level on the anode or the cathode, then it will go through a fill cycle. And assuming there is pressurized water connected to the test system, that water will enter into the humidifier in a controlled fashion, bring the water level back up to satisfy the alarm condition, and you will not get an alarm at all. That's how the system is intended to work. So you should still have the alarm enabled because, for example, if the water is not connected to the test system, so for example, someone disconnects the water supply pressure, either depressurizes the water supply or disconnects it completely, then you could still end up with an empty humidifier, a humidifier empty of water, and we want to avoid that situation. So you still want the alarm enabled, but typically you're not going to get an alarm because the system will take care of itself in terms of satisfying the water level in the humidifier. Did that answer the question? I don't see the chat. I don't have any feedback, so I have no idea whether.
I think it must have. I don't see another question.
Right. Excellent. Okay. Yeah. So there's a few sort of options here. You know, you can enable or disable some of these things depending on exactly on how you want the test system to respond on an alarm condition. Excuse me. This is talk very briefly about the temperature watchdog. This is a relatively new feature that was enabled recently. Basically, the request was from a customer who said that, well, sometimes we forget to put the heaters in the cell. So this is like a PEM cell where you've got these cartridge heaters that are used to heat the cell. And they said, well, sometimes we forget to put the heaters in the cell fixture itself. And so they're sitting on the bench top, but they're connected to the test system. and we apply heat, where we try and heat up the cell, and the cartridges get very hot, and we end up with a dangerous situation, either potential fire issue, or we at a minimum we end up scorching the bench top, and also you don't want someone to pick up a hot heater. And so they said, well, can you basically, can you make it so that if the temperature of the cell doesn't start to rise, that you can stop the heating process, right? So it's kind of an extra safety feature. And so that's what we call the temperature watchdog. And this just allows the customer to basically, if for some reason this is enabled, so what it's looking for is looking for a 2-degree rise in temperature within 60 seconds. If you try and apply, start heating up the cell temperature, start to heat up the cell, and you don't satisfy this ramp rate, then it assumes that there's a problem. The heaters aren't in the cell fixture, right? Because in that case, you're not going to start to heat the cell. Another example would be if the thermocouple is not in the cell. So let's say the heaters are in the cell, but the thermocouple isn't, then you're not going to register the fact that the cell is starting to heat up. And eventually the cell would overheat, right? It would run away because the thermocouple just is registering sort of ambient temperature. So that's another example. So you want to stop and throw up an alarm, and that's what would happen there. So that's the cell temperature watchdog. And basically this only works if the temperature is less than 40 degrees. So the limit says if the temperature is higher than 40 degrees, then even if you don't satisfy the ramp rate, you don't get an alarm. So for example, you might not be able to maintain this ramp rate at very high temperatures. And so you don't really want that alarm to take effect if the cell is approaching 120 degrees and it's not really changing 2 degrees every 60 seconds, right? So everything's working fine, just because you don't have enough heater power, the temperature rise is slowing down. You don't want an alarm condition based on the fact that the temperature is approaching its set point. So we have a limit here. So basically the idea is here, if you're starting from ambient and you don't see the ramp rate, you don't see the temperature change, then you're going to throw up an alarm because something is going on, something is not quite right. Looks like you can set a standby temperature if you do have an alarm condition. I've never used that, and I'm not sure, I've never used this either. I'd have to look in the manual as to what that is as well. So that's the alarms. Nothing really changes in terms of the window here, so I'm not going to exit out of here. We'll go to the temperature follower next. This only applies for test systems. Well, this is primarily used for test systems that have the heated, temperature controlled heated lines. So an 850 does not have temperature controlled heated lines. They are constant power, so we do not use temperature followers. The 840 does. So let me bring up an 840 rendering. All right, so an 840, which is the big brother to the 850, higher current, higher flow, higher power. It's a more costly device, and so we have the ability to control. We have a little more cost built into the unit. We have the ability to control the temperature of the lines. Right, so these lines have thermocouples in them, and they have dedicated temperature controllers. Okay, and so we're controlling the temperature that these heated lines run at. And typically the way they're used is they're run in what we call a follower fashion. Because the intent of the heated line is to prevent condensation, what we want to do is run those lines at a temperature a little bit higher than the humidifier temperature to prevent, so we don't get condensation, right? And so if the humidifiers are at 90, sorry, let's say the humidifiers are at 80, we might want to run them, say, 10 degrees higher. That would be a very common situation. And so we basically have a bunch of different followers here, and these would have addresses associated with the two temperature controllers in the 840. So let's say it's 43 and 44, just as an example. And we're going to run them at the temperature associated with the anode humidifier for the anode line, same temperature, but add 10 degrees centigrade. And on the cathode, right, so we're going to run the cathode line at the temperature, a multiplier of 1, so at the same temperature as the cathode, but add 10, okay? So that would set, if the humidifiers are both at 80 degrees centigrade, that would apply a temperature set point of 90 degrees centigrade to the anode and cathode, right? And that's typically how they're going to be operated. I mean, it could be something different. It could be 5 degrees, something like that. You can have additional ones. I've never seen a system that has a bunch of followers. Oh, I guess I can imagine some situation where you'd have a lot of temperature controllers in which you would be using additional follower temperatures. But basically, the primary example would be an 840 that has temperature controlled lines, and the humidifier, the temperature at which we run those lines is going to be a function of the humidifier temperature, basically running at 10 degrees above that value. If we say yes, save. Okay, so let's see here. So now we should have a few more temperatures. Okay, so there we go. So now we have additional temperatures, but they're not really controlled, right? They're defined, the temperature at which they're going to operate is defined by the set point of the humidifier. So let's set 80 and 70 as the anode and cathode temperature for the humidifier temperatures. So now when we say apply temperatures, oh, it doesn't work. It doesn't work in demo mode, but basically anode would be 80, this one would be 90, cathode would be 70, this one would be set at 80 degrees. It just doesn't seem to work in the demonstration mode, but that's how that would show up. And of course, you can disable them. So that's the temperature follower. Impedance and potentiostat. Pretty much any test system that's used nowadays, is if it has impedance, it's going to have one of our impedance analyzers, the 880 or the 881. Older systems, which worked with an external FRA like a Solitron. You tell it which type of impedance analyzer is connected to it, and take it from there. But that's typically, it's either going to be not available or it's going to be a Scribner FRA. Not really much to configure there. If you had a customer who's working with an external impedance analyzer and you're having problems, the best thing is just to contact us, and someone like Matt or the software engineer would help get that set up. And that's going to enable the impedance setup, impedance analyzer, as well as to give you the impedance experiment within the experiment list. The potentiostat. So the early versions. So our potentiostat is called an 885. It doesn't work. We don't have control of any other type of potentiostat other than our own potentiostat, which is the 885. The earliest version was just the 885. Then we came out with what we called the high-speed version, which was a USB-based potentiostat. And the latest generation is the G series, which is both a potentiostat and a galvanostat. And so we can enter the serial number. Again, that's going to be provided on the rear panel of the 885 potentiostat. So this is how, let me just show what that looks like in practice. So on an 850, again, we have a video about this. Installation and use, or not really use of the 885 potentiostat, but that's how an 885 potentiostat looks when it's installed on an 850. It's connected to the right, I guess if you look from the front, it's connected on the right side. And it's nice little accessory that adds a lot of capability for doing mostly for diagnostics of fuel cells. Things like hydrogen crossover, fuel crossover, electrochemical surface area measurement, durability type studies where you're looking at, say, catalyst degradation or catalyst support degradation, things of that nature require a potentiostat, not the load in the 850 or the 890. This is the potentiostat for installed with an 890. This would be something like in an 840 fuel cell test system, or for people like Toyo in Japan, or HEFIS in Taiwan and in China. They do test systems built around 890s as opposed, well, sometimes. And so they get an 890 and there's a horizontal version of an 885 that sits on top. So basically that's the hardware. And then this is configuring the software. So basically just telling it what it is. So now,
Hi, Kevin.
hello.
Hello. Hi, this is Sutirtho from Batsol. So I have a quick question in this potentiostat. So if some customer is opting for 881, then he need not to go for the EIS potentiostat, right? He can just get the 885.
No. So basically, if so the new version, great question. Thank you for allowing me to clarify that, although this isn't really about the hardware. The new version of the 885, the G series, the gray version, is the new series of the 885 is impedance compatible. It has two major changes from the old version. Anything that's kind of tannish in color. One, it's got current control mode, so it's both a potentiostat as well as a galvanostat, if you will. So you can do current control, not just voltage or potential control, and it's impedance capable. It's an option, just like in the 850. It's an option whether or not the equipment has the impedance analyzer installed in it, and because you're not using the load in conjunction with the 885. You're not using the impedance analyzer in the load in conjunction with the 885. They're completely separate instruments. If you want to do impedance using both instruments, you have to have the impedance analyzer in each instrument separately. So it's an option in each. So just because you have the impedance analyzer installed in the 850, that doesn't automatically give you impedance capability when you're using the potentiostat. So that's an option within the potentiostat itself. Thank you for allowing me to clarify that. So now we have a new window associated with basically alarm limits for the potentiostat. Typically, it's going to be a 2 amp unit. If it's a vertical version, which goes with the 850, we do have a 5 amp version, which is typically going to be used with like the horizontal version for an 890 or in an 840 type setup for higher current. But so anyways, you can reduce the limits of the potentiostat, at which point you'll get an alarm. If you want, again, it's for the protection of the cell. It's not to protect the test system. You're not going to hurt anything in terms of the test equipment itself. It's for the protection of the cell. Say you have a small cell and you don't want to drive it beyond plus or minus 1 amp, something like that, right? Or you don't want to drive it to more than plus or minus 1 volt, or maybe 2 volts on the positive and negative 1 volt on the negative, something like that, right? So it's for protection of the cell. With that, you're going to get the potentiostat related experiments. Remember, anytime you want to use an experiment that runs the potentiostat, it has to begin with P-stat or G-stat. Right, so this is the new version of the potentiostat, has current control, or P-stat / G-stat, where we can mix between current and voltage control, and it's for specialized scan and hold type experiments. And of course, now we have, I want to do that. And of course, we're familiar with the impedance analyzer setup, right? So if we don't have it, this window and this button goes away. And then I think there might be just, so that's the PStat setup and impedance analyzer. Really not much. You basically just enable them. There's not really much really to do here other than choose what type of potentiostat, and it can auto detect if you want. And then the final thing is the 892 and configuration of the 892. The 892 is a data expansion unit. So let's say you want to have additional type monitoring devices connected to the setup. This might be, for example, independent pressure transducers. Sorry, every time I click over, it goes away. You have additional pressure sensors in the system. Say you want to look at pressure drop in the cell. So you would have a pressure transducer, a pressure sensor upstream and downstream of the cell. As long as those pressure sensors have an analog output, they can be connected to something called an 892 data expansion unit. The 892 itself has 8 thermocouple inputs, 8 temperature measurement. So if you want to say look at temperature, if you have a large cell, for example, a large format cell, hundreds of square centimeters, and you're getting gradation in temperature within that cell, you might have, it might be instrumented with a bunch of thermocouples to look at temperature profiles within the cell, or it could be within a stack, for example. You might have multiple thermocouples in a stack to look at temperatures at different locations within that stack. And then, so these are temperatures, and then these are the analog inputs. So any device that puts out some sort of analog signal, 0 to 5, 0 to 10 volts, 4 to 20 milliamps, so those sort of common type analog outputs, they can be connected to the unit as well. And then this is where we configure it, right? And we can actually have multiple 892s on a single test system, but most common would be one 892. As you show in the figure, it's kind of broken into 2 sides, right? There's one side that's dedicated to thermocouples and another side that's dedicated to analogs. We also make a 16-channel analog version as well that sometimes primarily HEPIS has used in their test systems that have a lot of additional inputs. And so you can think of the unit as being broken into 2 halves. Module 1, which is on the left side, that's the thermocouples, looking at the front, that's the left side. And then module 2, which is on the right side, and that's going to be our analog inputs, right? So these are typically going to be either a voltage or say a pressure. And so the right side, enable module, right? So there's our temperatures. In this case, because it's already configured, you don't have to do any scaling and there's no offset. These are just thermocouple. You just label them, you know, different locations within your stack, for example, right? Cell 1, cell 2, whatever. The analog side, the analog input side, you're typically going to configure it. If it's a straight up voltage, then it's fine. You can just leave it as that. But if it's a pressure sensor, let's say it's, you know, it's anode, let's do anode inlet. So this would be upstream. And let's say I want to do it in kPa, right? So I have a pressure sensor that say, let's say it's 0, let's say it's a 500 kPa, so like a 5 bar or 5 atmosphere pressure transducer. That's the full scale. And let's say it's a 0 to 5 volt, right? So that would be 100 kPa per volt. So if the pressure transducer puts out 0 to 5 volts, 5 volts being 500 kilopascals, then the scaling would be 100 kPa per volt, and the offset would be 0. If it's a 4 to 20 milliamp output device, then there's a scaling factor and an offset factor typically. And I could have, you know, I could have multiples. I'll just do say anode outlet, right? So I'm going to look at pressure drop across the cell. And it's also the same type of device. Let's say this one is a 250 kPa full scaling. So that's going to be a a scaling factor of 50 kPa per volt if it's a 0 to 5 volt output device. And then I'm going to disable these so they don't show up. Okay, so let's just hit save yes. And actually this brings up a good point because I'd forgotten to mention that throughout all of this, as we've added different accessories, we've new parameters have shown up on the far right hand side, and I'll get to that. So when we have an 892, we end up with what we call an auxiliary signals section, right? And again, we can choose to record them or not, just like any other parameter. There's our 8 temperatures, and then there's our inlet pressure sensor connection, and our out. Oh, I spelled it wrong. The outlet pressure sensor, right? And so we can that would be that by looking at the pressure difference between the inlet and outlet, we can get at the pressure drop in the cell. So that would be a configuration of the 892 within FuelCell. Let's see here. Oh yeah, so right. So now we've got in our fuel menu. We go back to the. We've got gas mixing on the anode. We've got a multi-gas. We've got wet dry, and so we've got parameters associated with that, and we've got pressure, right? So we've got an automatic back pressure system. So that has its own pressure transducer. So we're gonna be able to record anode pressure in kPa. We can record whether we're using the wet or the dry mode, right? Again, so 1 is wet, 0 is dry. So we would see a 1 here when we're in the wet condition. For the multi-gas, it's going to tell us is it basically A, B, or C. I believe it's just it doesn't say what the gas is. It just says A, B, or C. I believe is what you see here in terms of that, and that can be recorded. So I know I have a record in my data file as to what gas is being used at what point. For gas mixing, I can see how much of each gas is going to be end up being provided to the cell based on what I'm using in terms of gas mixing. So I don't have anything in the cathode section, so there is no cathode mix section, but if there was, it would show up down here. I only have an anode gas mix section, gas mixing section. So let's see, is there anything else? Yeah, I think that's about it. So additional parameters, yeah, aux, and then mostly associated with the fuel. Oh, there is an auxiliary temperature, right? So we have the auxiliary temperature controller here, and that's going to show up under the cell section. Yeah, so that's fuel configuration, or sorry, that's instrument configuration. I'm going to stop, and I'll try and answer any questions that you have. Marion, I don't know. I can't see the chat. I apologize. So let's see.
Yeah, I can see it. I don't see any questions. Does anyone
Okay.
have any questions?
Yeah, I have a couple of questions. I'm Shutirtha again. So just for the 892, the analog inputs, can
Yes.
they be used for to measure the stack voltages?
Yes, you can use it as a stack voltage monitoring device. Yes, because fundamentally the inputs on the 892 on the analog side, those are they're typically either going to be a voltage input or current input, and it depends on how you wire the actual connector and how it's connected. But yeah, you could monitor the you could just straight up monitor voltage. If it was part of a stack, you could monitor. Yes. Good question.
And I also see that these analog inputs, they have certain, I mean, say at least 4 or 5 voltage range, right? 150 millivolt, 500 millivolt, 1 volt, 5 volt, and 10 volts. Hello.
Yeah. You're looking at the data. You're looking at the data sheet.
Yeah. Yes. So these ranges are selectable, or I mean, like it is a fixed one for a particular 892 input?
That's a good question. I'm not sure. I'd have to ask Matt about that. You've quickly revealed my limited knowledge. I don't know. I've only ever used them as either 0 to 5 volt. I don't know if they come pre-configured. It's a great question. Why can't I see? Oh, I'm the wrong place. I'd have to ask the talk to Matt. I'm sorry, I don't know the answer to that.
Yes, because in the software, actually, we do not have the option for selecting this range, right? So that's my.
Let's see here. Input voltage ranges. Yeah, it looks like it's probably a factory configured. Yeah, my guess is that you're exactly right. You probably it's probably something that we set here at the factory. The default would probably be 0 to 5 volts.
Okay.
Perhaps. I'm not exactly sure. So if you wanted to, I know the same thing can be used with like the 4 to 20 milliamp range.
Yes.
Yeah.
Okay.
Yeah.
Okay. So, and another question, which actually I am referring to your flow bench schematic for 840. So you said that, say for the gas mixing, when you were explaining the gas mixing unit, you said that if there is a corrosive gas, we have to do additional plumbing so that it goes directly to the cell.
Yeah. Yes, that's a statement. You have a question?
Yes. So then, I mean, like, can the gas backflow to the cathode humidifier? Is there a possibility?
Right. So yeah. So you need right. So you'd want to think about the possibilities. And that's a very good question. Yes. You typically would want some kind of check valve
Okay.
to prevent backflow. That's a really good question. So you want to avoid the possibility that that corrosive gas could sort of flow up back into the test system, right, via the line.
Okay.
Yep.
Yes.
So you would use a check valve.
Well, okay.
Yep.
So
Yep.
that also has to be part of this plumbing. I mean, users plumbing.
Yep. That would be part of the plumbing. I mean, we don't, so typically that's not, unless, I mean, if someone asks us to, they say, hey, we're gonna be using this gas and we're working with an 850 or an 840. And we know we want to plumb it directly to the cell. Can you provide a check valve? Sure, we can do that if we know ahead of time, but that's not like we don't provide that kind of hardware. Typically, that would be something that the customer. It's a simple thing for the customer to go find a check valve, right? So typically, we're not going to do that. But I mean, certainly, if we understand what they're doing and they ask for it, then we'll be happy to throw a check valve in there. But yeah, that's exactly what you're thinking about, is a check valve.
Okay. Thanks. That's all. Yep. Thanks, Kevin, for your answer. Yeah.
Good question. Thank you.
All right, Kevin, we have another question. Is there a difference between the EIS modules between the 881 EIS and the 885 plus EIS?
So Danny, that's the same module. It's the same hardware used in the 880. Sorry, the 850 as is used in the 885. They're both the 881. Now it's the 881 FRA. It's the same hardware. But because we can't share, we're unable physically. We're unable to share a single FRA between the load in the 850 or 890 and the 885 potentiostat hardware. We can't share hardware. So if you want to do impedance with both instruments, each instrument needs its own FRA. I know it sounds redundant, like we're making you buy. Well, we're making you buy 2 FRAs. Sorry about that. We're not able to share a single FRA between the load and the potentiostat, but they are physically the same piece of hardware. I mean, each device has its own physical hardware, 881 in it.
Kevin, so in that case, if you like to measure the impedance, when you use in a potentiostatic measurement, you need to have to use the FRA on the potentiostat, and all the other the rest of the times, for example, the HFR is done through the load.
Yes, that's correct. Yeah.
Okay.
Yeah. So typically, you're going to use the impedance analyzer, the 880 in the load when the cell is running as a cell, right? So you've got some current. The cell is under load, and you want to do impedance at some operating condition of the cell, right? So hydrogen, air, cell, the fuel cell is a fuel cell. It's generating electricity, power, energy. You've got current, and then you can measure the impedance at some operating condition, right? But we can't measure impedance at open circuit because we can't drive the load above open circuit, right? So we can't measure impedance at open circuit, because if you think about it, we're taking the DC condition, which is zero current, and then we're applying an AC on top of it. So in some sense, think about it, we have to be polarizing the cell above open circuit in a sinusoidal fashion, right? Above and below, right? The load can't do that. The load can't source any energy or current to the cell to drive it above open circuit. And so we can't do impedance at open circuit. And we also can't do impedance when the cell isn't running as a cell under load. So for example, if the cell is running with, say, hydrogen and nitrogen, right? So the cell is no longer an energy producing device. This is a typical stoichiometric again. So with hydrogen, nitrogen, now the cell is going to be purged with hydrogen and nitrogen. The open circuit's going to be more like 0.1 volts. We couldn't do impedance under those conditions using the load in the 850. We'd have to use, but we want to do impedance, we'd have to do it with the potentiostat because we're driving the cell under these conditions, okay? So an example would be doing catalyst layer proton resistance, right? So something that people are really interested in studying these days is what is the resistance to ionic transport of protons within the catalyst layer? It turns out that you can do that measurement you can determine what that is doing impedance under hydrogen nitrogen conditions. But you need a potentiostat to do that, and it's an EIS based measurement. We could also do EIS with the potentiostat at open circuit, right? So now say the fuel cell is working with hydrogen and air, so it is an energy producing device, right? So we have an open circuit of around 0.9 volts, and we want to do impedance at open circuit. We can't do it with the load, as I just mentioned, but we could do it with the potentiostat. So we could do an impedance-based experiment with the potentiostat in either, let's see, where's the impedance? Oh, so it's not showing up here, but there would be a P-stat, G-stat impedance experiment step if the potentiostat had the impedance analyzer, the 881 FRA, then I would have an experiment that would be associated with the P-stat, which would be an EIS experiment, and I could choose to do that, and I could do that at open circuit using when the fuel cell is running as a fuel cell, but at open circuit, no current, and I could get the impedance of the cell at open circuit. Does that answer your question, Danny?
Yes, absolutely.
Thank you
very much. Yeah,
Yep.
yeah. Thank you very much.
Yep. All right, we're coming up on 2 hours here, folks. Everyone's probably tired of hearing me talk. Any other questions before we end?
I don't see any other questions. So.
All right. Well, I'm going to say thank you very much. We really appreciate you taking the time to join us. I hope it was informative and helpful. Everyone have a good rest of your evening, day, morning, whatever it is, wherever you are. And thanks for tuning in.
Thank you very much, Kevin and Marion.